So in the previous video, we talked about the different oxidation states that you can have between alcohol going to aldehyde. And if we're talking about a primary alcohol, that can eventually be oxidized up to a carboxylic acid. So I wanted to give a little bit of sense of the difference in properties between these types of compounds. All right, so what I'm going to do here is just kind of compare butane to propanol to propanal to propanoic acid. All right, and just FYI, why am I comparing a 4-carbon something to a 3-carbon something? That's because in all of these we have this extra oxygen here. So if we wanted to keep the molecular weight somewhat similar, it would be a better comparison to do butane to a propanol. All right, so so starting off with butane, just plain old. This is going to be the most reduced form in this series right here. It has a boiling point of 0 degrees Celsius, right, which is a very, very low boiling point. All right, and the reason for that is that when you've got butane, if you imagine a bunch of identical molecules like this next to each other, there's not really a whole lot that would cause them to be attracted to each other. The major force that would cause these to be attracted to each other is London dispersion forces. Hopefully you recall that from earlier discussions on intermolecular bonding, intermolecular forces. But recall, these are the weakest of all of the intermolecular forces. All right, and they're so weak that this stuff, if you just put some of this in your hand, there's enough heat from your hand to turn that liquid into a gas. All right, in fact, it would feel very cold in your hand. All right, butane, by the way, is the stuff that's in cigarette lighters. Moving up one oxidation state, going from an alkane to an alcohol. All right, and by the way, this would be an oxidation of, this would have to be propane if it were to be oxidized to propanol. So notice that you go from 0 up to 98. You get a huge jump in the boiling point. And the reason for that is that alcohols are capable of hydrogen bonding. All right. Again, if we were to draw a bunch of alcohol molecules near each other and draw the delta positive, delta negative areas of slightly positive and slightly negative charge, you'd see that there's areas where hydrogen bonds can form. All right. So going from propanol up one oxidation state to propanal, notice that you get a drop in the boiling point. All right, and that's because if you compare this to this, you'll notice that hydrogen bonding is not possible. All right, generally with hydrogen bonding, you're going to need to have a hydrogen which is connected to either a nitrogen, oxygen, or fluorine. All right, and in this case, we don't have a hydrogen which is directly attached to that oxygen. All right, so there is a type of interaction which is stronger than an alkane, which is a dipole-dipole interaction, where if you draw the delta positive, delta negative, if you had two of these molecules, you could see that they could interact that way, and that's why the boiling point here of the aldehyde is higher than the alkane, but it's still not as high as the alcohols. All right, and that's because the alcohols can hydrogen bond, but the aldehydes cannot. All right. One thing about this relatively lower boiling point is that aldehydes tend to have be pretty aromatic. A lot of them have very flowery smelling odors. All right. In fact, this compound right here, propanal, is got a very flowery smell. All right. So going up one oxidation state from there to propanoic acid, notice you now get a huge increase in the boiling point. All right. So the reason for that is that this is capable of hydrogen bonding. All right. If you drew the delta positive, delta negatives, it's going to be even more pronounced in this bond here in the carboxylic acid than it would have been here. All right, and that creates very strong attractions between its neighbors. All right, so Carboxylic acids tend to have relatively high boiling points because of that.